have already prepared the solutions here, right? I'm just going to put it in the machine right now. You can see that these are all the solutions as specified on the screen, right? You can compare it. It's the same kind of like a Tetris arrangement, right? Right. So the same order. Right, don't gonna mix up, and you'll be surprised to see, hey, how come got 3 caps only, right? That's because this immobilization itself is going to be sequential. It's going to do the flow cell 1 deactivation first. Well, then that will take about 20-25 minutes maybe before it moves into immobilization, right? So I don't want my reagents to be exposed to air, you know, or too much environmental exchange, and I also don't want the client's protein to be exposed to the environment. Right, maybe they spend their whole life purifying this tiny amount, but I don't know, whichever lah. So you just put 3 caps lah. The rest of the reagents like ethanolamine, anti-tube, all that doesn't matter. This tool is going to be used immediately, so it's not going to be critical. Right, so I'm just going to close it. Right, I'm just going to get the rack here. Right, and then I'm just going to slot it on. Right, so you can see it's being slot on already. Then on this screen here, I'm going to click next. Right, you'll complain and say, oh, there is no rack, incorrect rack. Instead of actually, it's no rack at all lah. Just click change. Then it's going to open the chamber where you can just slide it in. Click. Yeah, sounds good. Alright, let's click OK. And then just click start. Right. Save template. Right, this July's folder. Right, this is called mob. Type mob mob. Right, of MERS on cell 2. Right, this is something that I usually abbreviate. Let's copy. Just click save. Right, yes, save outside, and then I'm going to paste the same name here. Right, just click save, and then the instrument will start the whole process. So you can see it's going to take 56 minutes. Right, and oh my god damn, look at the time now. It's 6:56 p.m. So which means that by the time this ends, it's going to be close to 8 p.m. Right, so remember, in biocore experimentation, please arrange your schedule so that you don't have to stay late lah, you know. But for me, no choice lah, because today is a busy day, you know. I could only start the whole process about 5+, like meetings and blah 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 blah. Right, so but when this is just making its own funny noises and getting to start, I shall just show you a few pedantic things or OCD things that I do with on SPR. Is that when you use the SPR instruments itself, I always buy the tips. You know, buy the tips. Right, the tips are bought. Right. These are not filled by any FYP or any other form of human slavery you can find, right? Yourself, you know, maybe fill it yourself, but usually we don't, right? And that's because these tips itself, when you purchase them, certified, you know, clean and all that, right? Very good for SPR, right? And some users come to me with tips, you know, they say, oh, I autoclave the tips and great for SPR. I said, no, that's very bad, because the SPR, the autoclave is not chemically clean, right? You autoclave the tips and then you dry it in the oven. If you smell the tips, you can smell something, you know. So there's a lot of broth, spilled broth, and strange things that are coating the tips, right? So that is actually not clean lah. So don't do unclean stuff, you know. Don't risk it, right? You purify the proteins and did all that stuff so far to this SPR experimental stage. So please use tips that are as clean as you can. Right, buy them. Not very expensive. It's only like maybe $3 a box or something. So don't waste your efforts, you know, and all that. Right, same for tips wise. Right, we also buy them, right, like this. We don't use a lot of the SPR tips nowadays. That's because the biocore tips, right, which are located, you know, over here. Right, these tips are incredibly narrow. Right, so what happens when these tips are incredibly narrow? Right, when they're very narrow, right, let me just show you an example. Your pipette tip itself, right, will almost never be able to get down to the bottom of the tube. You can see, right, you can see it's never at the bottom. So when you dispense poorly, you often will kind of like end up with undesired bubbles. You know, let me just see if I can replicate something like that. Right, so I have a tip here. I have a tip here filled with some PBS. Right, I'm just going to put it into the tube. Right, so I'm just going to put it in a tube. You can see, and then let's see what happens. Right. Oh, this is a good example. You can see all the liquid went down to the bottom. There's no bubble at all. Right. But many times people, when they fill their samples with a bit of surface tension and all that, right, they end up with a small bubble at the bottom. It kills the experiment. Right. So these tips itself, right, if you need to fill them, but we always fill it in some ways like at a certain angle. Right. Let me just show you. Trying to prop the phone up again with this bottle of buffer. Right, and wait, I need a rack to keep the phone from rotating. It's not heavy enough. This is okay, fine. I shall use this. Right. So what is the way of filling a tube? You know, is that you can always either consider getting tips that are slightly longer. Like I like this branded tips here, right? But these tips are a bit rare. Right, and these tips are also special. They have this rubber head here. It's supposed to use for multi-channel pipette lah. Right, but one good thing is that these sort of tips, right, you would actually easily get down all the way to the bottom of the tube, right, but not perfect yet. You see, there's still a space lah. So sometimes you get problems filling. So how to prevent problems? Very simple, right? Just take your pipette tip, pick up some buffer, right. And then as you fill the tip, right, please hold it like this, and then give a simple, don't fill it vertically, fill it as sideways, right, and then with the tip pointing downwards like this, right, you just give it a quick squirt in the beginning before you eject the rest of the sample, and then this quick squirt, right, will spray some small amounts of liquid at the bottom, so it will prevent the bubble from forming, right. So learn this trick lah. So all your samples will be bubble free. Right, if not, and then of course when sample go inside, right, don't think of recovering it because you can't pipette all the way. Right, no matter what, it will still have a bit left. You can see, right, you can get everything out. Right, so this is something that you have to be mindful of. Right, so you can see that over here, if I don't fill properly, right, you can see there's a bubble. So you can focus or not. There's a bubble at the bottom of the tube. Yeah. So when there's a bubble at the bottom of the tube, right, this will be bad lah. Right, for the experiment. You see? Right. Yeah, not so clear. See, this is just an iPhone taking a video, so that it's not so easy. You see a bubble lah. Right, so a good one, a well-filled one, you will have no bubble. Let me show you a good one. Yeah, right, this is a good one. You can see the bottom. Right, no bubble. Right, side by side comparison. If I can take two out at the same time, you can see which one has a bubble at the bottom. Right, you can tell lah. Right, so don't underestimate the problems that these bubbles can give you. Right, beautiful curves, publishable curves. One-shot success in experiments is always desired. Right, so try to maximize your chances in this miserable research world. Right, you're always spending your time and efforts, right, and not want it to go to waste. Right, so this is how you want to work with the samples. Right, and then now let's go back to the screen. Alright, on the screen itself, what's going on now? We are having our aiming coupling. Right, so I'll just zoom out. Right, so the aiming coupling event is ongoing. Screen is stuck. Right, is it not going to focus? Okay, this is not so good. Okay, yeah, finally focus. Fine. Right, so what happens in this experiment here, right, is that it will actually start transferring substances from A1 into empty vial at A3. After it transfers some from A2 to A3, this is essentially transferring EDC and NHS equal volumes. Right, and then pipette up and down, mix, right, and then after mix ready, right, then you mix ready, you will inject your NHS EDC into the system. Right, so if you look at the system here, right, NHS itself should give you a boxy curve lah, right, and then it should be flat lah. The best systems are best maintenance, right? Usually the box is so flat like it's like 90 degrees lah. But some people instrument maintenance not so good, or temperature fluctuation like me over here sometimes a bit of aircon all that, right? You do have a bit of a baseline drift. Right, but of course in experiments doesn't really have bad problem because the drift is the same in all 4 channels because of temperature, so it doesn't create any obstacles for you lah. Right, but in any case you can see that for this we have not too bad lah, almost 90-degree box, so okay lor, happy lah. Right, so but of course nothing much to be too happy yet because it's just the first control flow cell activation deactivation mah. Right, so with this control flow cell activation deactivation, how beautiful it is, it's not going to create any impact for science. It's just going to be just in record that you just did a good surface deactivation itself. Right, so the important thing will happen after this, which is on flow cell 2, right, in about 10 minutes time, or maybe a bit more. Right, yeah, 10 minutes time or so, yeah. And that's where you see the important thing happen. Right, so far so good. I think this is just the basics for immobilization. Right, so there are some questions that I can address right now, right? And some people say, hey, why don't I use streptavidin avidin capture to capture protein for small molecule interaction, right? Maybe in some other video later on I will explain the problem with that, right? But before that I will also say that streptavidin capture, haystack capture, and all these other strange capture methods that Michael has, right, doesn't allow you to capture a lot of material on the surface. So if you're working with interactions where the mass differences, right, between the one on the surface and the one floating across is so big, right, then you won't want to have too little lah, right? So when you cannot immobilize a lot, your signal very small, you can't get your curves, right? Sometimes affinity not so high, signals very small also, so you can get your curves as well. So having a high immobilization sometimes is just a simple thought process lah. Right, so in SPR experiment design, if you say back to ground zero where you have no SPR experience at all, right, just simply ask anyone, don't think of perfect curves from the start, right? That itself success rate maybe 5% so far lah. 1 in 20 projects give you perfect curves, blind, just anyhow inject, perfect, and publish already. But 95%, right, our experiments need a bit of reiterations. So the first thing to always make sure that you can show your boss or anyone, right, is that when you immobilize a protein or do an SPR experiment, you want to say yes, no, can we see the binding, right? So a yes, no experiment, right, may not give you the nicest curve shapes, right, but it will give you a confirmation that yes, there's something that we can work with lah, to perfect or polish, right? I have a diamond that is rough and I can polish it, right? So if let's say your simple high immobilization, you don't see a binding event at all, right, then you're somewhat doomed, that you can't do much unless you revisit the interaction and find out why it's not binding, something went wrong somewhere, and troubleshoot the whole tedious process lah. Yeah. So usually for small molecule interactions, we tend to want to immobilize a lot. Yeah. So this is how it is. We'll just stop it here.